For this lesson, we'll be going over memory devices. Well, first let's cover what is memory. Memory, also known as addressable memory, is a system entity for storing binary code for instructions and data. Memory consists of various amounts of elements, which generally latches or charges/discharges via capacitors. Now for this lesson, we'll be going over common types of memory, and it's going to be broken up into volatile and non-volatile memory. Volatile memory is going to be RAM, which is random access memory, which is going to be broken up into static RAM or dynamic RAM. And then we have non-volatile memory, which is typically your read-only memory, ROM, and then that's broken down to programmable ROM and erasable PROM. Now let's go over volatile memory first. Volatile memory stores data until power is removed. The typical form of volatile memory is known as random access memory, or RAM. Now think of RAM as the notepad of the memory world. When your microprocessor performs calculations or movements, it uses the RAM to store this data temporarily while it performs these calculations, and then it reuses it as needed, similar to a notepad. Now there are two types of RAM, static RAM and dynamic RAM. Static RAM uses logic circuits to hold its ones and zeros, and this memory is usually known for its speed. Dynamic RAM uses capacitors, so it must constantly be refreshed just to keep its data, or else it will be lost. This memory is known as for its capacity due to the fact that it uses very few components compared to static RAM. Now getting a little deeper in the weeds for volatile memory, we also have what's known as cache memory. This is very similar to RAM, however it's relatively smaller and high-speed RAM that goes hand in hand with your microprocessor. Now SRAM or static RAM is typically used for your cache memory. You can use dynamic RAM in its place, however, we need speed because this is for your microprocessor calculations and any data movement. Now cache usually consists of two levels. Its first level is known as primary cache. This is usually because it's internal to your microprocessor, and that would probably be your fastest of the two. You also have your second level cache, and that's usually external to your processor. However, it's usually closer than where your main memory is, your main RAM. Now let's go over the second flow chart, non-volatile memory. Non-volatile memory stores data even after power is removed. The most common type or form of non-volatile memory is known as read-only memory, or ROM. ROM is typically used to hold small amounts of repetitive instructions or data and cannot be rewritten like RAM is. It's not a notepad. This is written in stone type information. The most common applications used for ROM is for storing firmware. Just like volatile memory, non-volatile memory also has subtypes. We already talked about read-only memory, ROM, and this is memory that is programmed already and it comes from the manufacturer that way. After that, we have programmable ROM, PROM, which is similar to ROM, however it's a blank slate. It comes delivered to you unprogrammed so you can store whatever data you like before installing it into your circuit board. Next, we have your rewritable section, which is your erasable PROM. This is typically data that can be rewritten once it's erased. And then that has subtypes. Electrically erasable PROM, and this can be both erased and programmed with electrical pulses. And then you have ultraviolet PROM, which the data can be erased when exposed to UV light. This is typically a chip that has a circle on the top where you has a piece of tape over it to pretty much keep it from being exposed to UV light. Anytime you want to erase it, you remove that piece of tape. Now also in the non-volatile memory area, we also have what is called flash memory. Flash memory falls under your floppy disks and small hard drives. Even though this is non-volatile memory, this type of memory is mostly known as storage. So I won't be going into details for flash memory because it just falls in a different realm of memory. Now that we're familiar with memory type, we can start going to memory capacity. Memory is made up of storage elements called cells. Each cell retains a memory of bits, in other words, your ones or your zeros. Your cells are then compiled into blocks or memory arrays. A little visual aid in front of you here, we have in the middle, we have 4 different arrays. An 8x8, 8x4, 32x1, and then a 3-dimensional one, which has 8 rows, 8 columns, and then it has a 4-bit depth. That's going to lead you to the array format you may see in your textbooks. You may see row by column by depth, which is your bits, or you'll see address bit width times the number of bits. So look at the example at the very bottom here. We have red, which is your number of rows or your address bit width, And then you have in blue, which is going to be your bits, which is your data or your words. So let's just say you have an address bus that has 15 bits wide. So it's going to be 2 to the 15. That means you can have 32,768 addresses. And then the number of data bits you have, which is 8. Now this is also going to lead to the common term you may hear for memory size. You're not going to hear 32,768 bit or bytes. You're going to hear 32K, 64K, 128K bytes. That's because the memory size is referred to the number of words based on a power of 2. Now in the previous slide, we talked about your address bus and your data bus. Well, what does that mean? The location of memory stored is known as your address. The address is generally identified by the row location, in other words, what we have in red. This location is selected via address bus, and then the data that is read or written to this location is communicated via data bus, which we have in blue. Now, right now I have in the illustration, I have a line with a slash through it and a 3. That shows you how many bits that bus can actually hold. So anytime you see that, that's how many bits you're going to be using for that particular bus. So in red, I have 3 bits, and then for my data bus, in blue, I have 8 bits. Now this last slide was created to cover some loose ends, because this is usually the area where people get tripped up. We talked about how memory devices are constructed with data buses and address buses, but they also have signal select pins. The 2 common signal select pins are the read-write pins and the chip select pins. Read-write is usually indicated by an R/W or WE, and this determines if the chip is in read mode or write mode, and you'll typically see this with RAM. The other pin is chip select, also known as chip enable pin, and this is indicated by a CS for chip select or CE for chip enable. This selects the memory device or enables it in a sense. Now you want your chip select pin to be high to enable the device. However, this is where everyone gets tripped up. A majority of memory devices have a not over the chip select, in other words your dash, meaning the pin must indicate a low or 0 to enable the chip. And we'll go over this a little bit more in some of the example problems. All right. We're going to start off with a very easy one here. This is something a little out of the ordinary what I'm used to doing. However, this is to get us a little familiar with the different types of memory devices. So we're going to play the I am game. Basically what we're going to do is, based on the description here, we're going to match it up to the memory device to the right. So it's a matching game in a sense. For example, we'll start with the first one. I am small but very fast, ideal for taking notes from the brain due to my location. All right, so let's look what we got. It's relatively small. It's very fast, and it takes notes. Well, takes notes, the first thing that comes to mind is RAM, because RAM takes notes from the microprocessor or the CPU. And the CPU is also known as the brain. So right there, I'm thinking of RAM. So it's either 1, 2, or 5, because like we talked about, 5 is a little bit deeper in the weeds as far as RAM. And then it says based on its location. Well, based on the slides, we know that cache can be internal to the microprocessor or be very closely external to the microprocessor, levels 1 and 2. And it's very small and very fast. So I'm going to say for the first one here, it's going to be this guy right here. So I would say this guy is number 5. So it's cache. All right, so let's do the next one. I am very fast at taking notes, but I take up space and cost more. Again, it goes back to RAM. So we're going to look at these 2 guys right here. So it says I take notes, I'm very fast, but I take up space and cost more. We know DRAM actually has a large amount of space. However, it costs less because it takes up less components, because this consists of a capacitor and a transistor. So it takes up less space, which means it costs less. And it actually takes up less physical space to give you more data space. Whereas static RAM is very fast. However, it takes up more physical space because it has more components, and that which means it also costs more. So I would say for this guy is static RAM. All right, next one. I am sensitive to sunlight when I'm not taking cover. All right, well, right away, I'm going to say that's pretty much a freebie because, like we talked about on the PowerPoint slide, when you have ultraviolet programmable read-only memory, anytime you take the piece of tape off, You can expose it to light, or in this case, ultraviolet light, which is sunlight. So which means, I'd say that guy is number 6. All right, next one. I am fast and great for storing small amounts of information while the CPU powers off. So when the CPU powers off, so right there, I'm thinking it's non-volatile memory. So the only two non-volatile memories that are not taken up are these two guys right here. It says I'm fast and great for storing information. So I'm going to say it's probably between these two. Unfortunately, I'm not really sure which one yet. So I'm going to put a pin in that one and we'll go from there. Let's go to the next one. I'm made with a blank slate, but when told, I will perform tasks the same always. Well, again, that sounds like read-only memory because it performs tasks always. However, it's made with a blank slate. Well, programmable read-only memory comes from the factory blank, which means you as the consumer would actually program it before putting it into your customized circuit. So which means this guy is number 4. And that also means that now we can go back to this guy right here and say this one actually mimics read-only memory because it's the last non-volatile memory. So that guy right there is number 3. And of course, process elimination, let's look this over. Great for storing large amounts of data, plus I'm cheap. Sadly, I take notes slower than most. That is a perfect description at a gram. It does store large amounts of data. It is cheaper because it uses less components. However, it is slower than static RAM because it has to constantly refresh, and charging and discharging capacitors takes time. So, right then and there, we have DRAM. So this example is just to get our feet wet with the different types of memory devices. This is relatively simple, but it's to get you familiarized with what they're used for, as well as just little facts. All right, let's go to the next one. All right, for our next example, this one we're going to step it up a little bit. We're going to determine the memory capacity to obtain 128 megabytes, and we want to know how many bits are actually stored in that answer. All right, so let's go ahead and look at these one at a time. We have A through D. We have 4 different arrays, and we want to know which one has 128 megabytes. Well, let's just go over a few facts. 1 byte equals 8 bits. So right away, you want to look for either a column or depth of 8 bits just equal a byte. So we want to look at the actual total answer as far as in byte form. So anytime you see a big B, that's bytes. Little b is bits. So we'll look at this first one. We have 16K for rows, and then 8K for columns. Well, right here, if you multiply those together, it's actually going to give you 128 meg. However, we don't have bytes, we have bits, because if you multiply those together, you're actually getting every individual cell. So you have 128 megabits. Unfortunately, that's not going to fly, because if you divide this by 8, that's how many megabytes you're going to get, which means you're going to come out to be 16 megabytes. I'll put a meg right there, that way you see what I'm doing. So that's not it. All right, let's look at this one. You have 128 rows, and that's meg, times 4 bits of columns. And if you multiply those together, that's, again, how many bits you're getting. So 128 times 4 is going to give you 512 megabits. Well, unfortunately, you do the same tactic. 512 megabits divided by 8 is going to give you 64 megabytes. Still just a little shy. If you added 4 more columns, you'd be able to come up with your 128 megabytes. Unfortunately, that's a no-go. Well, let's look at this guy. We have 16K rows, 8K columns, and a bit depth of 4. You're looking at an answer of also 512 megabits. And of course, if you divide that by 8, it's going to give you the same answer as over here, which is 64 megabytes. So unfortunately, that one's a no-go. It had more, it was actually a 3D version, however, still wasn't enough. Well, let's look at our last one. We have 16K rows, 8K columns, and then we also have an 8-bit depth. So there's 8 blocks right here, or 8 extra arrays right behind it, which is times 8. Well, if you multiply those together, it's going to give you an answer of 1 gigabit. And of course, if you divide that by 8, it's going to give you an answer of 128 megabytes, which is what we're looking for. So right there, our answer is D. Now the next question is, how many bits are actually stored in this answer? The numbers we're playing with here is our figure of speech memory. It's what our power of 2 memory is. This is what anytime you go buy it from the store, what you're paying for or what you're actually asking for. But in reality, the amount of bits you're actually receiving is different. So let's do the math. Let me clean up these guys real quick. Start off this guy right here. So anytime we refer to 16K, we mean 2 to the 14th power. And that's how many bits you have. Same thing with 8K. Anytime you have 8K, we're going 2 to the 13. And you can plug and chug this in a calculator and it'll give you the same answer. And anytime you have 8 bits, put bits, that way it's easy to see, it's going to be 2 to the 3, because 2 times 2 times 2 is 8 bits. Because anytime we refer to these numbers, we're talking about powers of 2. Now the question is, how many bits are we actually getting in this total array right here? Well, if you look at this, 2 to the 14 times 2 to the 13 times 2 to the 3, well, if you go back to your basic algebra classes, you can always add these guys together. So it's 2 to the 30, which means if you plug and chug that in our calculator, it's going to give you 1,073,741,824 bits. So in reality, that's how many bits you're getting. Now, how many bytes are you getting? Are you actually getting 128 megabytes? So let's go ahead and divide this by 8 real quick, just for out of humor me department. Actual total bytes you're getting, your word lengths you're getting, is 134,217,728 bytes. So you're not getting 128 megabytes, you're getting 134 megabytes. So this example wasn't really too bad. This just gets your feet wet of how to determine your memory capacities, as well as to get you a little bit familiar with the terminologies as far as megabits and megabytes. Let's do one more problem. All right, for our last example, we got ourselves a fun one. We're going to determine the data output if the address bus supplied a binary number of 110. Well, looking at the illustration we have a random access memory and we have a read-only memory chip. So we have 2 different chips, and we have both an address bus going to it, which we can tell it's our address bus because it's going to the address pins of these 2 memory devices. And then we want to know our data output, which is this guy right here, of the 2 devices. We have a binary number of 110. Well, if you're looking at it in decimal form, that comes out to be 6. So that's base 2. So your binary number of 110 is a address of 6. Okay? So we know right away, anytime this calls for an address of 6, it's going to be going to either this guy and or this guy. Okay? Now the other thing we need to look at is we need to look at our chip enable or chip select pins, because both of them have 2 different values. Right now we have ROM with a 1, and then we have a RAM with a 0. Well, as we said in the PowerPoint, our chip select needs to be a high to be enabled, because you want these chips enabled to provide you your data. Well, the only problem is you have a not symbol over this. So a high actually requires a low input. So in this case, we're looking for a 0 for it to be enabled, which means our RAM right here is enabled. And going to our ROM, we have a 1, which is a high input. That's going to actually disable your ROM memory chip, which means this one is not going to supply data at all. It's just basically being disabled. And we also have a 1 right here on this particular pin, which is a read-write pin, and it looks like we're reading from it. Since we have a high, it looks like it's reading, because if it was low, it'd be writing, because due to that not symbol right there. So looking at this, we're looking for an 8-bit output. This looks like 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. And we want it on address number 6. So it's this guy right here. So which means our data output is going to be 0, 1, 0, 0, 1, 0, 1, 0. So that is going to be our data output with 8 bits. And if you want to convert that to decimal, it's pretty simple. You can actually use your calculator for this one if you'd like. And it gives us a decimal of 74. That's a base 10, of course. The situation was reversed. And let's just say this was actually a 0 and this was a 0. That means you can actually take the data from your ROM and it'd be writing to your RAM because you put it in write mode. So which means your address 6, which is right there, this 011000100, would actually write to your RAM. Because right now they're both enabled. However, this is now in write mode. So all it's doing is taking data and plugging it into this guy. So that's just a little food for thought as far as how to understand how these chips work. Well, if you have any questions, feel free to let me know, and I hope you all have a good day.